We also have on this worksheet this one, reversible heating, that's described as adiabatic. And so let's think about this for a second before we jump into calculating anything. The first thing that should jump out at us is that it is adiabatic. And when we have adiabatic changes, adiabatic describes the wall between the system and my surroundings as that part of the universe that's under study. And our systems in this case are the perfect gas, so I usually draw it in its little piston cylinder arrangement, but we'll just think about it like this for now. This wall, in an adiabatic change, and a closed system, first of all, so there is no matter going out or into my system, and everything is matter or energy. So in a closed system, I'm allowed to transfer energy to excuse me, to and from my system, from the surroundings. And so that means I can heat, cool, compress, or expand. Now, adiabatic immediately tells me that Q is 0, because it's really a description of the wall between my system and surrounding, and it tells me that it is insulating. It's not conducting of heat. And so with Q 0, how can I have an adiabatic heating process? Because heating implies that Q is greater than 0, that Q enters the system, that energy enters the system as heat. But adiabatic dictates that if the change is adiabatic, that dictates that Q is equal to 0, so this can't be true. And so this was just on the list of writing down everything that we had talked about, all the different reversible, irreversible, and all the different kinds of changes, heating, cooling, compressing, expanding, and all the different kinds of conditions. And we were just putting all of our combinations together. This one, however, doesn't make any sense, because these two terms are incompatible with each other, heating and adiabatic. So because heating implies that Q is greater than 0, and adiabatic implies that Q equals 0, then, once again, off the list.